Okay, so matrices are basically just systems of equations without the letters, the equal signs, or any of the other hoopla. To convert a system of equations into a matrix, you literally just take all the coefficients. 2, 1, 2, put your answers over here. 3, negative 1, oh, excuse me, negative 5, negative 1, 4, 1, negative 2, negative 3, negative 6. And boom, you have done the first system. You've just converted it into a matrix, and that's all it wanted you to do, just to see if you could do it. That's it. Calm down. You have done the first one. If you are missing a letter, you just need to put in a 0 for it. Now, let's look at like number 5. Number 5, I could see a lot of people missing because they would just take the numbers directly where they lie in the problem. But what you need to remember is these letters, like this first column is X, second column is Y, third column is Z. So just because the X's on these second two equations are written in the middle, their numbers still go in the X column. So that would be 5, 1, 2, negative 2, 1, 0. 0. Yeah. They're the X's. We're on number 5. Yeah. And then negative 3, 0, negative 3. And then 0, 5, 4. The big thing, just make sure all your letters are in the same column. That is going to be extremely important for when we start working with solving using matrices. That is what we're doing today. You want to go ahead and try number 7? Try number 7. I'll do it up here and we'll compare answers. Yes, sir. It just makes it easier. Yeah. Well, because if I may coin my own DOM, embrace the matrix, it can make a lot of things easier for you that would normally be hard. I don't understand where the numbers are coming from. Well, I know where they're coming from, but I don't know why we bother doing it like this. Yeah. It's literally just to simplify. That is the entire function of a matrix, is just to simplify it, so that we don't have to worry with the x's, the y's, the z's, the equals. It's just to say, here's what you're focusing on. Just look at the numbers. Well, he's done it before. Well, you won't fail this time. Unless, of course, you make a bunch of excuses. But you won't. It's your student of the month. All right, so. Great expectations. I'm sorry. I'm waiting for you all to do number 7. And then we're going to compare answers. Yes, it does. Once you get your finished product, if you want to compare it with mine, hopefully it's the same. Raise your hand if you're getting anything different. Oh, dang. Oh, touche. I thought that was you're correct. What you're seeing there in that Z column, that's what we're going for all day. We're going for a 1 in one of the columns and a 0 in the other. So that probably makes no sense until I actually teach this. But you're going to learn to love the sight of that. Yay. Okay. Questions about any of those? All we're doing is taking a system and putting it into matrices. Guess what the next slide is? No, we're not going to do any of that today. I guess we could. No, we're going in the other direction. We're going to take matrices, convert them into systems of equations. So like number 11 would be 1x plus 1y plus 4. Dang it, I left out w. 1w. Sure. Plus 4y plus z equals 3. Please don't. Negative w plus x minus y. I just leave blanks like that. That way I can keep my letters straight. 2w plus 5z equals 11. And 12y plus 4z. Thank you. And there you go. And number 9, I'm just going to write it in shorthand to save time. I'm not going to leave the blanks or anything. Questions about where these are coming from? So all we're doing right now is just converting back and forth. Question? Yes. No. I don't really care. Okay. So if there's no questions, let's just keep going. Now, calm down. Just relax. It'll be alright. Let's take this problem. Let's look at number 1. Now imagine matrices had nothing to do with this. Eeny, meeny, miny, Sarah. If I gave you problem number 1 yesterday and I said solve it, what would you do to start solving it? What letter would you start going after? There's no wrong answer here. Why? And what would you do to that? Oh, that's a by 5 you mean? Oh, the bottom one. Okay. So you would multiply the top one by 2 and add it to the bottom one. Same thing in a matrix. You're going to multiply the top one, top row, that's a row, the other one's a column. Multiply the top row by 2 and add it to the bottom one. That's how you would write that in matrix notation. You multiply the top row by 2 and add it to the bottom row. Plus 3. Yeah. Now, whenever you write these little matrix notations, the one that's actually being affected, and I'll explain what I mean by that in just a second, is the second one. What does he mean? I'll show you. Let's come over here to this one. Number 15. Very, very similar to the one Sarah Beth just said. We're going to multiply the top row by -3 and add it to the second row. Now, when you write your finished matrix, because it wants you to rewrite the entire matrix after the given operations that they tell you to do. Now, whatever one's written last, this is the one that's the one that's changing. R2 is the one that's changing. R1 will not change when you rewrite your matrix. So it would be 1, -3, 2, just a second. Alright, try this again. Sometimes it works better if I write on the top of the board. Okay. 1, -3, 2, and 0. Row 3 is not changing. It's not mentioned anywhere here. 2, -2, 1, and 3. And what do we say? -3 times the first row plus the second row. Now the way I do that to keep it straight, I don't care how you do it. I like to go back to this one and just write it in there. So -3 times row 1 would be, let me change colors, would be -3, +9, -6, and 0. Multiply -3 all the way across. Now I'm going to add that to the second row. 0, 10, -7, 7. Because, well, just think about when we were solving these yesterday. What did you do? You took 2, put them together, and you just got 1, right? That's essentially what we're doing today. You only get 1 product. And the one you are changing will be that product. What? That's right. Now, why did we do this? Same reason she did it when she explained it to me. She was attacking the y. This one was attacking the x. And we just canceled an x. That's what we did. Now, to be more clear, if we had another a system right next to it that we were watching this happen on. But now we have one equation that's nothing but y's and z's. Now, let's just think for a second here. It didn't ask us to do this, but had it asked us to solve the system of equations, we just got rid of one x. We need to get rid of another x. What does somebody think would be a logical next step to solving this? I'm sorry? That's right. We would multiply the top row by -2 and add it to row 3, and then that would be a 0 as well. And we would have two YZ equations only. Just the exact same as yesterday. The only difference is you don't have to think of it in terms of X, Y, Z. You just go for 1 is a good thing, 0 is a bad. 1s and 0s are good things. What?
So if you were to say try to get rid of x's with row 1 and row 3, you would do -2 R1 plus R2.
Yep.
Yeah, I don't understand that. Okay. If you do that again, you check the first row to say you still have an X.
I'll explain that in a minute. We're building up to that. To go back to what you said, you don't understand how we got here?
No.
We literally multiplied the original first row by -3, which I wrote in right here.
But then why did you write the other?
Because we didn't change the first row. Again, it's like yesterday. We took two equations, added them together, and got one finished equation, right? Well, so we only have one finished equation, so we only want it to take up one row. So we choose which row we actually want to morph into what we want. I think it'll make more sense when we start solving them, when we actually are solving one. Let's just practice a few more row operations, and we'll do some more of what you're talking about. So like 17. What are the only two rows that are actually changing on number 17? Row 3 and 4. So I'm going to rewrite my 4x4 matrix. You keep your heads up. All right. So row 1 and 2, I'm going to rewrite just as they are. 1, -1, 1, 1, 3. 0, 1, -2, -1, 0. Now, to change row 3, multiplied this one by -2 and added it. So I'll write it right above it. Multiplying the top row by -2 would give you -2, +2, -2, -2, -6. Adding that to row 3, you get 0, 2, 1, 2, 5. Oh, okay. Now we're going to do the same thing. Multiply the top row by -5. Add it to the bottom row. So I'm going to write that right above it. -5, +5, -5, -5, -15. I did. That is what I did. I'm just writing it here so that the addition will be very easy for me. That's just how I solve them. You might solve them differently, but that helps me keep track of what I'm doing. Yes. I just like to put it right next to it so that the addition's right there for me. So, and again, you might not want to do it like that. That's just how I keep it straight. So it's 0, 6, -3. Stop freaking out, then. -1, -9. Questions about where I got any of that? Now, had we started solving this, what would we have? We would have had a 4x4 system of equations that we have just reduced into now a 3x3 system of equations. The goal, and what we're going to be doing today, we're going to get 1, 1, 1, 1. Everything else 0. Because if you think about writing, once you have 1, 1, 1, 1, and everything else 0, if you were to take that out and rewrite that as a system of equations, what would that be? That'd be W equals this, X equals this, Y equals this, and Z equals this. And you'll have solved it. You'll have solved that system of equations without ever worrying about letters or anything like that. That's where we're going.
What if it said -2 R2 plus R2? So you multiply the second and the third and the third.
-2 R2.
Yeah, so
So you multiply the second row by negative 2. Add it to row 3. Only the third row would change. That's correct. Yes?
Have you ever had row 3 as your row 2? Like when it's say negative 5 times row 3 as your row 2?
In the same step? No.
Like, say that negative 5 is all 3. How would you use the one you wrote?
That's a good question. Here's the thing. You know what? That'll make more sense when we actually start solving these. If you just want to wait 2 seconds, that's the next slide, and I think it'll make more sense then. All right. That'll be a bonus today. Okay. Now we're going to do just that. We're going to do exactly what we just did, and we're actually going to use it to solve a system. So, number 21. Let's first write it in matrix form. Yes, ma'am. What do you mean? Oh, good question. If there is just, remember how we said as long as you do something to one side of the equation, you can do it to the other and everything's cool? That's what that is. Let's say row 1 had been 1/2, 3/2, 5/2, like fractions. Actually, that's bad again. Let's say it had been 2, well, what is it? It's all even. Is there something that factors out? If this equation were to be 2x minus 6y plus 14, 10, does something factor out? 2. So they're saying, well, let's just reduce it. As long as you do something to an entire row, you can multiply whatever you want by these at any time, and you haven't changed. Exactly. Exactly. Like, what made this one so simple to cancel? The fact that this is just a 1, right? So we can just multiply something by it, add it to the others, and they'll just filter out. Well, what if this row had started as 2, negative 2, 2, 2, 6? Well, a 1 is the best, because you can use a 1 to get to anything. So we could have divided that row by 2, just like this, and then done that stuff. So this is just what they call a scalar, a number that's just multiplied in, and it just changes the scale of your equation, but doesn't change the equation at all. So, are you asking me what would the answer look like? That would be the only one that changed. These two would stay the same, and this would be 1, negative 3, 2, 5. Yes, ma'am. The row that changes. No, that's a fluke. We're going to be writing those ourselves, and that's not something I care about. If it's just this, and that's obviously the only thing changing. If it's addition, or I guess you could do subtraction, but I don't know why you'd want to, then it's always going to be the second one. Yeah, that it's actually written here. Well, we're going to write those today. So I don't really care where you write it. I mean, I guess you could do it like that to keep it straight, but you don't have to. No, but then, yeah, it's probably a pattern. Yeah. All right, so number 21. 1, 1, negative 1, negative 2. 2, negative 1, 1, 5. Negative 1, 2, 2, 1. That's our little barrier separating our answers. Alrighty. Now, just like before, first thing you have to do is identify which letter you want to start attacking. Where you normally want to look, now this one you have a wide variety of options, but if you might have some today where there's a whole matrix of numbers and then just 1, 1. You want to use 1s as much as possible, because they're just the easiest thing to do. You know, if we had a 2 and a 3, just like yesterday, we'd have to multiply this one by negative 3, and this one by 2. But if you have a 1, you can just multiply that one by anything to get rid of anything. So, but as we have a 1 in all 3 columns, so it doesn't really matter which one we start with. So Braden. That did. You start with the one that did. Which column you want to start with? I don't even care. First, second, third. Second one. All right. So we're getting rid of two of our, basically our y values, just like yesterday. Getting rid of our y's. Is there a first step that makes sense to people? Yeah. I could just go ahead and add row 1 and row 2, couldn't I? Row 1 plus row 2 would completely get rid of this guy. Now what we're going to do is we're going to combine steps today. We're using this guy to get rid of these two. So what could I do to get rid of this y? Negative 2, row 1 plus row 3. I'm going to do both of those steps to get to my next matrix. So the first one's not changing. 1, 1, negative 1, negative 2. Now row 1 plus row 2. That'll be 3, 0, 2 zeros back to back. And 3. And then negative 2 row 1, which I will write right here so I can keep it straight. That'll be negative 2, positive 2, positive 4. Adding these up, that's negative 3, 0, 4, 5. Oh, right. Right. Now, biggest problem people run into when they're solving it like this. Biggest problem. Would you agree that at this point we have eliminated all but one y, which is what we want? We used row 1 to get rid of the y. See that? We will not use row 1 to get rid of any other letter. It's imperative that you remember that. Why not? Let's say we try to use this z to get rid of this z. What would happen? If we multiplied the top row by 4 and added it to the bottom row, we would put a y right back in there. You would fill up this column again that we just emptied. So you are not going to use row 1 to get rid of anything from here on out. You have to use row, not row 1. Yeah, you'll have to use row 2 or row 3. Yes, you do. In fact, well, right now, how would that equation read? 3x equals 3. So what actual matrix operation could I do to reduce that? 1/3, row 2. If my next step was 1/3, row 2, that would give me 1, 1, negative 1, negative 2, 1, 0, 0, 1. 1 is what we like. Negative 3, 0, 4, 5. You're right, x is done. Now we can use that x to solve for the z in the bottom one, can't we? Alan, what step am I going to do that, to cancel out that bottom x? Positive 3, you're right. 3 row 2 and add it to row 3, right? Now we also need to get rid of the x value on the first equation. So what would I do to row 2 to get rid of the x value in my first equation? Yeah, just negative. So negative R2 plus row 1. And we're using the second row to wipe out our x's. Yes?
Why couldn't we do like on the top blue matrix then? Why couldn't you just do addition to get rid of the x's?
You mean like row 2 plus row 3?
Yeah.
You could have. You could have. Before you simplified it, that'd be fine. But Hannah pointed out, hey, x is done, so we took that step. But you could have. He brings up a good point. Well, before we reduce this, why couldn't we just add these two rows as they were to get rid of, because it's already 3, and you could have, and then reduced it. That's fine. But as it is, let's see. Let's see, which row is not changing? Row 2? 1, 0, 0, 1. I'll change colors. All right. 3 times row 2 plus row 3. So 3 times row 2 is going to be 3, 0, 0, 3. Adding that to the bottom row, that's 0, 0, 4, 8. It's the first one. We're not touching it. We're using it to change these rows.
So whenever if I would like to write down the movement of the first, how many equations possibly become?
When you say the equation, you mean this equation? Yes, that's correct. Now, when you have one like this, McKenna, where it's just all by itself, then obviously it's changing. But when it's being applied to a different one, it's the first one that doesn't change. So that'll give us 0, 0, 4, 8. Now we're pretty much done with the z column too, but we'll get to that in a second. All right, then we had negative row 2 plus row 1. So I'm going to rewrite negative row 2 right above it. That'd be negative 1, 0, 0, negative 1. Adding that to the top one, you get 0, 1, negative 1, negative 3. All right. Now, what would our next step be to go ahead and reduce this bottom row? 1/4. Yeah, 1/4, row 3, which would give us 0, 0, 1, 2. Now 2 of our rows are done. Two of our rows are done. Do you have a question? No?
You multiply that by 1/4 to get rid of that 4.
Yep. Because how would this read now? This would read 1z equals 2. So z equals 2. We have x and z. Now we're just looking for y. So we have to get rid of this z. Now notice, this should always work out like this. I used row 1 to get rid of the y's, row 2 to get rid of the x's. What's the only row I have left to use? Row 3. So what am I going to do with row 3 to get rid of row 1? Just add it as is. And that would wipe out this z value. So the only one changing is row 1. So, row 2 and 3 aren't changing. 1, 0, 0, 1, 0, 0, 1, 2. Sorry, I'm writing downhill. And adding those two, you get 0, 1, 0, 5. All three are done. Yeah, I got too big of a hurry. I got excited. Yes. Go back up. Yes. Here, we did negative row 2 plus row 1. So we added negative this row, which I wrote right here, and added it to row 1. Now, we're not quite done. X is not negative 1, Y is not 1, and Z is not 2. You need a diagonal. So, a very, very simple step from here is we literally just need these numbers to be along this. So I just need to switch row 1 and row 2. Row 1 is going to switch with row 2, giving me 1, 0, 0, 1, 0, 1, 0, negative 1, 0, 0, 1, 2. You see that diagonal form? You are now done. X is 1, Y is negative 1, Z is 2. And there's your ordered triple. You've solved the system via matrices. More or less. That's the whole point. Well, you could. That's fine. Your goal today is just to. Your goal is to solve. Yeah, when you're done, I just want to see an ordered triple or an ordered quartuple. There it is. That's all I want to see at the end of the day. Good news is you've only got like 10 problems today. Yes. I think 10? No, it's not. And there is a bonus. For those of you looking for extra credit, there is a bonus in today's lesson. Now, I will tell you this. Unlike yesterday, when it is so hard to go back and diagnose where you did a problem. If you do not carefully articulate what every step is, and I know some of you in here suffer from bad, I don't like to show work syndrome. I was the same way. But if you don't, you're going to have to start over every time because it will be impossible to backtrack if you do not show ample work. Just letting you know. Now, how can I check my answers? Yes, you can do these on the matrix, on the calculator. You know what? No. I'll show you this in the future. Yeah. I'll show you that in the future. I don't want to. Okay, does anybody want to do a 4x4 together? Okay. Well, we're going. So here we go. After you use, it's not necessarily the first row. Once you use a row to wipe out a column, like we did, because like when we go back, what did we do? We used the first row to wipe out the y's. Then we used the second row to wipe out the x's and get. Yes. If you have just 1, 1 and all the other zeros, then you have emptied it and you've done what you're supposed to do. But you cannot go back and reuse these again. or you're going to end up adding something back into a 0, which is like the opposite of what we want. Yeah. Ordered triple. Did you have a question? Because the 4x4s are much hairier doing what we did yesterday. Do we really do all this to get into 4x4s? It would be extremely daunting to do a 4x4 without using a matrix. And it's still going to be lengthy, but it's not. Anyway, I'll let you finish that sentence in your own words in your head. I really do need you to keep your heads up. All right. I might be gay, but I need you to keep your head up so one day you're here. All right. What letter are we going to attack? You want to attack the first column, second column, third column, fourth column? X. She just chose X. It doesn't matter. Okay. Now, so we're going to attack the first column. Which row do you want to use to do that? You can use the first or the third. They have 1s in them. First or second row to do that. So you want to use the first row. So you want to use the second row. Okay.
Why can't you just do add row 3 and 4?
Oh, I guess you could. Well, you'd still have to finish out the rest of the row, but if you wanted to start like that, you could. So, to get to our next matrix, let's see. Row 3 plus row 4 will be one of our steps. But, so that'll take out this one, but we still need to take out 2 of the others. So which row do you want to use to do that? This is the simple way. Okay. Go. Do it however you want to. No. It's alright. If you want to do it yesterday's way, go ahead.